Hello, class. Welcome back to another episode of some e-learning adventures. Before we get started, I just want to smack my lips a little bit. Okay, got that out of the way with. Let's get started. We're nearing the end of our fundamental force chapter. It was a short chapter to begin with, and again, it was kind of experimental because we're kind of rough drafting our first way, our way through this for the first time. So let's kind of end up here on our magnetic or our electromagnetism. So of the four fundamental forces, there's a strong force, the weak force, gravity, and electromagnetism. And from these four forces, you get every other type of force that you can think of: friction, air resistance, the tension that's in spring, and explosive forces that create thrust. All that kind of stuff comes from or stems from these four fundamental forces. As always, if you see anything in blue, you definitely write that down as some notes, and then you can use those notes as part of the Google form later on to check for your understanding of this section. If there's anything else that is of particular interest or you think helps explain things, then by all means write that down as well. Okay, first things first, let's talk about electric current. Um, Electricity and magnetism are very much intertwined. They're kind of like two sides of the same coin. So to have an understanding of magnetism, we should first have an understanding of electricity. So electric current is the rate. The current is a rate at which a charge passes by a point on a circuit. And a charge is measured in something called coulombs, the units of coulombs. 1 coulomb is equal to 6.25 times 10 to the 18th electrons. That is a very large number of electrons. It's right here written out in standard form. So it's a tremendous number of electrons. The unit of current is the amp. So you should be familiar with that, or ampere is really how it's called, but shorthand would be amp. 1 amp is equal to 1 coulomb every second. So if you look at a wire and you take a point on that wire, if there's a device on the other end of that wire that's drawing 1 amps worth of current, that means that every second this many electrons are passing through that point. Current is interesting. So current, there's a couple properties of electricity. Current and voltage are ones that should come to mind. Current is what does damage. Current is what kills you. Voltage is not that bad. I mean, it can obviously do a lot of damage, but it's not the voltage that hurts. It's not the voltage that kills. It's the current. So just to calibrate your senses as to what can do damage to you versus what can't. 0.001 amps is not that much. You probably wouldn't even notice it. If your skin was wet, it might conduct a little bit better and you would feel it that way. 0.016 amps is the maximum amount before you can't let go. So once you cross that threshold at about zero point 0.2 amps, that's when your muscles start to seize and you can't let go of something that's shocking you. A tenth of an amp is ventricular fibrillation. So your heart starts getting electrical signals and it starts beating rapidly or not in the rhythm that it's supposed to be beating at. 1 amp will lead to severe burns. 2 amps will make your heart stop. So it'll destroy it will cause cardiac arrest and it can burn your other organs. 10,000 to 200,000 amps, this is about the amount of amperage that's in a lightning strike. All right, so voltage, on the other hand, is something a little bit different. I'll talk about that in just a moment. 30 volts is what pushes current through your skin. So you need to have about 30 volts in order to get the current, the amperage, through the barrier of your skin. Um, 500 to 100 volts can be deadly if your skin is wet with high enough amps. 400 volts will actually start breaking your skin down. And 1,000 plus volts is the shock you feel from static electricity. But because it's so short lived, it doesn't do that much damage. It just hurts. It just shocks you. And then about 1 billion volts is a lightning strike. So when you couple a lightning strike with the amount of amperage that's in a lightning strike, you can understand why it's so deadly. Now, that being said, a lot of times lightning strikes or people get struck by lightning and they live. Um, which is to say that the strike is either not carrying that amount of voltage or that amperage, or your body is just not passing through you with enough time to do the damage that it needs to do to kill you. So speaking of that, let's talk about Roy Sullivan for a minute. This is the most unlucky man in the history of all things. He was born in Greene County, Virginia. That alone doesn't make him unlucky, but you know, one strike against you, I guess. All right, so he started working as a ranger in Shenandoah National Park in 1936. In 1942, in the spring, he was hiding from a thunderstorm in one of those, like a fire lookout tower on top of a mountain, and it was newly constructed, so there was no lightning rod. It got hit, he said, about 7 or 8 times, and the fire was jumping all over the place inside the tower. So he ran out, and was immediately struck by lightning. The lightning burned a half-inch strip through his right leg and hit his toe and then left a hole in his shoe. You can see a picture of his hat with a lightning strike or lightning burn in it right there. Well, that wasn't enough for old Roy Sullivan, so in July of 1969, he was hit again while driving his truck. Now, a metal body of a car usually acts as a Faraday cage, and it's kind of protects the passengers. But in this case, the strike hit a tree near the road and was deflected into the open window. The strike knocked him unconscious and burned off of his eyebrows and eyelashes, and then set his hair on fire. The truck came to a stop right before veering off of a cliff, or didn't veer off a cliff. It stopped right before a cliff's edge. Well, here comes number three. 1 year later, in July of 1970, Sullivan was struck while in his yard. The lightning hit a nearby power transformer and jumped to his left shoulder, searing it. Not enough for good old Roy. It is now spring of 72. Sullivan was inside a ranger station when hit again. This time his hair was set on fire. He rushed to a bathroom, but couldn't fit his head between the tap and the basin, so he had to use a wet towel to put his head out. After the fourth strike, he now was pretty much convinced that there was some force of nature trying to destroy him, and he actually started carrying a can of water around in case his hair was set on fire again. Well, a new year, a new strike. In 73, while on patrol, he saw storm clouds and he started driving away. He drove for quite a while and the storm seemed to be following him, but as he got far enough away, he got out of his truck when he thought he was safe. He wasn't. The bolt moved down his left arm and leg, knocking his shoes off. Still conscious, he crawled back to this truck and poured the can of water over his head because it was on fire. Well, once again, in the June of 76, he saw a cloud. The cloud saw him. He tried running, but he wasn't fast enough. And on a Saturday morning in June 25th, in 1977, Sullivan was struck again while fishing. This time the lightning hit his head, of course, set his hair on fire, burnt his chest and stomach. And as per usual, he started meandering back to his truck to get a can of water when something unusual happened. A bear came out and tried to steal the trout from his fishing line. He fended the bear off with a branch. Later, he said that it was his 23rd time he hit a bear with a stick in his life. This is the most unlucky person in the history of all things. Anyway, getting back to what volts are. Volts is what pushes electrons through a wire. It's kind of like a water tower pushing water down pipes. Um, the bigger the voltage, the bigger the pressure. 1 volt is equal to a joule, which is a unit of energy, divided by a charge, which is the unit of, or a property of a coulomb. A watt is how much power flows in a circuit. So a watt it's kind of like a rate because it's the amount of energy, which is a joule, divided by seconds. So when you have these three units or these three properties that we're talking about, watts, volts, and amps, this is how they are equated. Watts is equal to volts times amps. All right, so now let's kind of get to how this comes into play with magnetism. So when you have electrons going through a wire, it actually creates a field around the wire. It creates this magnetic field. So when charge flows, it creates a current and it produces a magnetic field. There's this rule called the right hand rule, where if you stick your thumb up, your pointer finger out, and then your index finger or your middle finger kind of perpendicular to that, that tells you the direction of current, which way the field is pointing, and which way the force is pushing on that field. Magnetism is a phenomenon produced by the movement of electric charge. So it results in attractive and repulsive forces between objects. Materials that can be magnetized are called ferromagnetic and consist of many magnetic domains. So if you were to zoom in way, way close to like the atomic structure of metal, you would see that there's these tiny, tiny little magnets that are that can be aligned. So in this case, we have the magnetic domains kind of unaligned and they're pointing in different ways. And in here, they're all aligned in the same way. So what this kind of looks like, the end result is that when you have a random assortment of magnetic poles pointing in different ways, all those domains on average will cancel out and your net force is going to equal 0. But if you can get all those domains to line up in the same way, then your net force is not equal to 0. It's kind of aligned and you get this net force that's unbalanced and you'll be able to get a force from that. What's kind of cool is I've never seen anybody with this, but I have heard of it, that some people insert, especially like electricians or people who work with magnets or electricity frequently, they insert tiny, tiny little magnets into their fingertips so that they can feel the magnetic fields in a wire. So if you have an implant, a magnetic implant in like the your ring finger, like this person does, and you put that next to a wire that has electricity going through it, you can actually feel an attractive or a repulsive force as you get closer and closer to that wire. I think that's kind of interesting. It's like creating a sixth sense in addition to your other five. Okay, electromagnetism. This is the force that creates electricity and magnetism by moving electrons. It is much stronger than the force of gravity. This force determines the properties of most objects in your daily life. It's the result of, or friction is the result of this. Thrust is the result of this. A lot of things um, are a direct result of how electromagnetism makes its way into your daily life. And it's interestingly, it's the only fundamental force that can repel. So gravity is attractive, the strong force, the weak force, those are attractive forces, but electromagnetism can actually push things away. I think that's it. Okay, so that's it for me today. Thanks for listening. If you have any questions, let me know, and then just follow the instructions in the rest of class to figure out how to fill out that Google form.